expenses. We are team number one, and today we're going to be presenting our PIA project for our topic subject study of change.
Our team project focuses on our parfum distribution business, 6 cent. We need to design an open-top shipping box to hold a fixed volume of exactly 4,000 cubic centimeters to safely fit our product. To keep the bottle upright, the base must be a perfect square. Our goal is to use calculus to minimize the surface area, which is directly lowers our packaging product cost.
Well, now we are continuing with the variables. Well, here, to model these mathematical, we establish our variables. We let the side length of the square base be measured in centimeters, meaning both length and width are equal. Also, we let the height of the shipping box be measured in centimeters. The volume is our constant target of 4,000 cubic centimeters, and the total surface area is what we want to minimize.
We solve this problem with two equations. First, the condition for volume is given by multiplying length, width, and height. Since the base of a square, this means the total volume equals the side of the base square multiplied by the height of the box. When we isolate the height, it becomes the total volume divided by the square of the side of the base. Second, the surface area equation considers the five faces of an open box, one square base, which is the side of the base squared, plus four identical walls, expressed as four times the side of the base multiplied by the height of the box.
To differentiate, our area equation must be in terms of a single variable, the side length of the square base. We substitute and isolate height expression into the area formula, multiplying 4 times the side length of the square base by 4,000 gives 16,000 times the side length of the square base over the side length of the square base squared. Canceling all the common factors, simplify our objective function down to the total surface area equals the side length of the square base squared plus 16,000 divided by the side length of the square base.
Well, now we're going to talk about the calculus optimization of our problem. For the calculation, we take the first derivative of our area function and set it equal to 0 to find the absolute lowest point of the curve. This gives us 2 times the side length of the square base minus 16,000 divided by the side length of the square bases squared equals 0. Now, cross multiplying gives us 2 times the side length of the square base cubed equals 16,000, meaning the side length of the square base cubed equals 8,000. Taking the cube root reveals our optimal side length of the square base is exactly 20 centimeters. Now, we need to plug in 20 back into our height equation, which gives an optimal height for the shipping box of 10 centimeters, giving us a total of 20 times 20 times 10, and we get the optimized square box.
To mathematically guarantee this is a minimum, we perform the second derivative test. Our second derivative is 2 plus 32,000 divided by the side length of the square base cubed. Evaluating this at 20 centimeters gives a result of positive 6. Because our result is positive, the graph is concave up, proving 20 centimeters is the absolute minimum surface area. For our classroom demonstration, we brought two boxes that hold the exact same volume of 4,000 cubic centimeters. As you can see, our optimized box uses only 800 square centimeters of cubic of cardstock, while the alternative use 1,700 square centimeters. This proves our calculus solution cuts production material expense by more than half.
Thank you very much for your attention. This was our Team PIA project, and we hope you liked it.